Sample problem number 11. This is a Newton's third law problem. This one is a little bit different than the other Newton's third problems that we've done before. So for example, the previous examples were one student pushing another, and then we had the action-reaction force happen on each individual. This is a third law problem, but has a little bit more complexity to it. Let's get started. A parent is pulling two children on two wagons that are daisy-chained together with a rope. The parent is pulling with a force of 67.5 newtons. The child in the first wagon has a mass of 15 kilograms. The child in the second wagon has a mass of 20 kilograms. And we're going to assume that each wagon has a mass of 5 kilograms each. What we're looking for is the acceleration of the entire system. And part B, we're looking for the tension in the rope between the two wagons. And we're going to do it from the perspective of the first wagon. And the second time, we're going to do it from the perspective of the second wagon. So we're going to start off with FP representing the force from the parent. And that's 67.5 newtons. And we'll make it positive because it's in the positive direction or the forward direction. Now, the next part, the mass of the two children plus the wagon. So what we have is the first wagon, we're going to call mass A. And the combined mass is going to be 20 kilograms. Where for the second kid, it's going to be their mass plus the mass of the wagon, which is a total of 25 kilograms. So we're looking for the acceleration and we're looking for the tension between both wagons from two different perspectives, from the first perspective of the first wagon and then from the perspective of the second wagon, or A and B. In this question, we're actually going to start off with a system diagram. This is not the same as a free body diagram, but what this is going to do is going to help us analyze a few things. So the big question has to do with the two ropes. So the first rope is this one. And this is where the parent is pulling on the first wagon. This is the second rope that is coupling the first and second wagon together. The total mass of the first wagon is less than the total mass of the second wagon. This is the debate. What is the relationship between FP and this tension? There are three possibilities. Possibility number one, that FP is equal to the tension. Possibility number two, FP is greater than the tension. Possibility number three, FP is less than the tension. So we're going to talk about a few things, how to conceptualize this, and to come up with a determination of what the actual relationship is. But before we do that, we're going to look for the acceleration of the system. Now, here is our assumption. We're assuming that this rope is not stretchy, which means that both objects are going to move together effectively as if they're one object. So what we can do is we can treat mass A and mass B as a single object. From the parent's perspective, the parent is towing both children. So whether or not they're connected by a rope, or if the two wagons were actually physically bolted together and it was basically one big mass, it feels the same from the perspective of the parent. But what we have to assume is that this rope is non-elastic. And the reason why we have to assume that it's non-elastic is because if it was, then the two objects would actually accelerate at different rates and you'd get this sort of weird bouncing back and forth. And of course, that makes it a much more difficult question to solve. So what we're going to do to solve the acceleration is that we're going to treat the system as a single mass. And that's why I have the force of AB combined. The force of the parent is accelerating in the forward direction. We're assuming that there's no force of friction. FNAB stands for the normal force acting on this combined mass of AB. This is mass AB combined, and this is the weight of AB. Technically, this is a non-collinear question because we have X component and Y component. However, it's a moot point, and that's because the normal and the force of gravity are going to mutually cancel each other out. And we know this because the wagons are not floating or sinking. There is no motion in the vertical, therefore there's no acceleration in the vertical. As a result, they cancel out to zero. So effectively, our F net acting on AB combined is just the X component, and it's equal to positive FP. Of course, thanks to Newton's second law, F net is equal to MA. But you're going to notice something, no subscript on the A. And the reason why is because the acceleration is the same for both objects, for object A and object B. Hence, no special subscript is required. Isolating for the acceleration, we know that MAB is attached through multiplication. The opposite of multiplication, of course, is division. And we get an acceleration of positive 1.50 meters per second squared. Now that we have the acceleration, we can solve for the tension in the rope between the two wagons. What we're going to do here for a moment is I'm just zooming out a bit here because I want to show you this. On the free body diagram of A, which means we're looking from mass A's perspective. So from the perspective of the first wagon, the tension in the rope is dragging it back or towards the left, if you will. But from the perspective of B, the tension is pulling it in the forward direction. This is the same tension, but they're happening on two different objects. Hence, this is why you have the equal but opposite. So this is Newton's third law at work. So let's see if we can logically infer what must be true about the relationship between FP and the tension. We know that the system is accelerating in this direction. The AX, well, which is technically the acceleration, is positive 1.5 meters per second squared. If that is the case, that must mean that the forces in the forward direction must be larger than the forces in the negative direction or in the backwards direction. Therefore, FP has to be larger than the tension. Let's solve for the tension by setting up our Fnet equation. So Fnet acting on object A. Again, this question is technically not collinear. So I've grouped the X components here and the Y components there. But the convenient thing, of course, is that the Y components cancel each other out because it's not floating or sinking, which mercifully makes our algebra much easier. Now, in the next line, we've dropped the vector notation. FP is positive, the tension is negative. Now, notice, I have already put the direction here. So the value for T now is just going to be the magnitude. But we have established that it is moving either to the left or backwards. We didn't really specify, but whatever floats your boat. So in this case, I decided to use left and right. Okay, so isolating for tension, we have to use SAM-DEB in reverse. And of course, we have three terms. This here being our term of concern. And since it is negative, I want to bring it over to the left-hand side. And at the same time, I'm going to bring this MAA to the right-hand side, which gives us tension is equal to positive FP minus MA times A, which gives us positive 67.5 minus 20 times positive 1.5, which gives us a magnitude for the tension of 37.5 newtons. But its direction from the perspective of A is 37.5 newtons to the left, because look at the free body diagram. It is moving to the left, and we also made it left right here. When we do it from the perspective of object B, we should get the same magnitude, but moving in the other direction, equal and opposite. Now solving from the perspective of wagon B. So we have mass B, and the real forces acting on it are the normal, the weight, and the tension. But this time the tension is moving in the forward or to the right, depending on your perspective. And of course, this is the third law. Conveniently, of course, the normal and the weight cancel each other out. So then we're just left with the tension. Dropping the vector notation, we've got MB times the acceleration of B, but we don't need the subscript B in this case. It's actually just just acceleration A, and we can get rid of this B as well. And that's because both objects are accelerating at the same rate. So that's MB times A is equal to positive tension, or tension is equal to MBA. Substituting in 25 times positive 1.5, and we get a magnitude of 37.5 newtons. And based on the diagram, we know the tension is to the right. So therefore, we get the tension is equal to 37.5 newtons to the right. And as you can see, every action has an equal and opposite reaction. And there's the third law at play. So in this example, we had just two objects. What if you have a situation with three? Well, let's take a look conceptually of what that's all about. So I have three random boxes here. We have a force acting on the first box. We've got a rope connecting the remaining, the first and the second, and then another rope between the second and the third. So labeling these, let's say this is rope 1, rope 2, and rope 3. And we know each rope will be under tension, and we use the capital T for tension. Technically, if you wanted to, you could write F subscript T for the force of tension. But in physics, when we have tensions, we often use capital T to represent the tension. And tensions are kind of a special force. And the reason why is because they only work in one way. You can't push a rope. You can only pull. So since they have this special property, we often just use a different letter to represent them. But it's just another way of saying a force. Okay, so the first rope I'm going to call tension 1, the tension in rope 1. This is the tension in rope 2, and this is the tension in rope 3. So what would be the relationship? Here, let's get that a little closer. What would be the relationship between these tensions? Which one would be the largest? Which one would be in the middle? And which one would be the smallest? A, B, and C, the 3 objects there. So now the easier way to think about this is what that would be like if these objects were being supported vertically. Instead of using a rope, let's use an analogy of a spring. So let's say we have a ceiling here, and then I have a spring. Let's do a little bit better job of drawing a spring. Okay, so now let's say we got our first object, and we want to attach it to the spring. Well, I think it's fairly reasonable to understand that the spring would stretch until it comes to an equilibrium. Now let's say we add another spring here, and then we add our mass B. Well, when we add our mass B, we know that that will cause the second spring to stretch a little bit, but now the first spring is going to stretch even more because the first one not only has to support A, but it also has to support B. Therefore, I think it's fairly reasonable to follow that the second spring doesn't have as much of a load as the first one. If we add a third mass with another spring, and if we were to attach it, clearly the spring would stretch, but in addition, now that B has C attached to it, the second string is going to stretch even more. And then the first spring, I think I said string accidentally, but the first spring is going to be stretched even further. So from this perspective, the first one is under the greatest tension because the first spring has to support A, B, and C combined. The second spring, although not under the same amount of tension as the first one, it has to support the mass of B and C. Not as much as A, but still it has to support the remaining 2 masses. And then finally, the last spring has it the easiest. The last spring is only supporting object C. So in this case, tension 1 would be greater than tension 2, which would be greater than tension 3. And the same thing applies here. The first rope is required to drag all 3 masses, but the second rope, it's only dragging the last 2 masses, and then the third rope, it's only dragging the 1 mass. And that is how we get that perspective on this type of third law problem.